So before we get too much into math stuff, um, I want to try to get a little admin out of the way. Um, a couple of things to mention. So our first test was supposed to be on Tuesday, or our first test. Our third test was supposed to be on Tuesday, um, but obviously that didn't happen. So it will be, I think, next Tuesday. So it'll be next class. Um, what that means is it's a little bit different than what it meant before. We're still going to have class as usual. So I will be still having a stream, and we'll go over some stuff. And at the end of that, I will hand out the test. I'll post it in Discord and I'll post it in D2L. And with that, you guys can go ahead and um, I'll give you a couple days to do that. So it'll be due at the beginning of the next class on Thursday. Um, and yeah, that's I'll tell you a little bit more about it once I hand out the test. But today, basically, we're just going to be wrapping up a little bit of stuff for applications. So in particular, we're going to be talking about linearization and maybe a couple other topics if we have some time. So, any questions about the upcoming test, or anything else that you want to ask about before we get into lecture stuff? Is maybe everybody's quiet? Maybe that's just me.
I don't know. Can you hear me?
I can hear you. Yeah.
Okay, I don't. I just jumped in. I don't know. I don't know if you were already talking about this, but when is the next exam?
The next exam is on Tuesday. We will have class before the exam. I do not know if that class is going to be review or it's going to be new material. If it's new material, it will not be material that will be on the exam.
Okay, perfect. Cool. Thank you.
Yep. Can I get someone else to speak real quick so I can check my volume?
How has your day been? I figured I was on mute again.
Yeah. Okay, so maybe the volume was actually on my end, not on you guys' end. So I think I've turned it up now, and we should be in better shape.
Fantastic.
Wait, Isaiah, can you speak again? You're very quiet.
I can't hear you.
Okay, well we'll figure it out as we go. Wait, let's go ahead and jump into linearization. Um, so linearization is it's sort of a fancy way of saying that we're going to basically a method of um, approximating things using calculus. So, for example, um, let's say that we wanted to know um, what is the square root of 4.1. The problem with finding the square root of 4.1 is that finding the square root of 4 is pretty straightforward. We all know it's 2. Finding the square root of 4.1 is a little bit trickier, right? Of course, we live in 2020. We could just plug it into a calculator. However, you can do what's called a linearization to have a sort of quick approximation of what it's supposed to be. So basically, linearization is we're going to take use a nearby known value of f of x equals the square root of x. In this case, f of 4 is equal to 2. Then we will use the tangent line to f of x at x equals 4 to approximate the value of f of 4.1. So if we want to think about this graphically, basically what we're doing is we're taking our function, which is the square root of x, which looks something like this, right? And we're taking the tangent line. I didn't draw a very good square root of x. Hold on, sorry. And we're taking the tangent line at this point here. Let's actually do that in another color real quick so we can see it more clearly. And we're going to use the tangent line to approximate what our value of 4.1 should be. So the first part of linearization and most of the calculus part of it is actually going ahead and doing the tangent line part, right? So let's find the line tangent to f of x at x equals 4. So we know that the point is, so x is equal to, x1 is equal to 4, and y1 is equal to 2. We know that we have to go through the point 4 comma 2. And what should the slope be? Well, the slope of the tangent line is the derivative. So we need to find f prime of x will be 1 over 2 root x. And then we'll plug 4 into that. F prime of 4 will be 1 over 2 root 4, which is 1 over 2 times 2, which is 1. So the tangent line equation will be y minus 2 is equal to 1/4 of x minus 4, or y minus 2 is equal to 1/4 x minus 1, and then we'll add 2 to both sides and we get y is equal to 1/4 x minus, sorry, plus 1. This is our tangent line. So let's go ahead and throw this up. Let's throw this up in Desmos because that's going to be a much better picture than I could draw by hand, right? So we can see here on the graph, right? This is where our tangent line is. So if we're close to the point at 4, our approximation is pretty good. You can barely see that red line there, right? You can pretty much, it's pretty much, they're right on top of each other, right? However, if we wanted to use this to estimate the value of maybe like the square root of 9, then our tangent line is going to give us a value that's totally false, right? Like if we try to use the tangent line to approximate 9, we get 3.25, and we know that the square root of 9 is 3. So
I have a quick question. What happened when you
yes,
added 2?
when I added 2, well,
Yes.
negative 1 plus 2 is 1, right?
Right. Sorry, I was adding 2 to the 1/4 x, which doesn't make sense.
Right. which we are doing. It's just we can only combine it with a -1, right? All right. So to make our estimation now, we want to find what the y coordinate should be of this line when we plug in 4.1, which is 4.1 over 4 plus 1, or 4.1 4 plus 4 over 4, which is 8.1 over 4, or maybe more familiarly, it would be 2.025. The actual value of the square root of 4.1 is 2.04. So the actual value, well, the actual better approximation that the calculator gives us is 2.0248. So we're pretty close. We've got 3 decimals of accuracy just from this quick linear estimation. So linear approximation is, or linearization is actually it's a special case of a much more powerful tool called Taylor or power series. Basically, I think I've alluded to this a few different times. I know I definitely did it in pre-calc, but one nice dream would be, man, it would be great if every single function in the world was a polynomial. Well, it turns out that if you're willing to accept an approximation, then we can kind of pretend that every single function is linear. We just need to have it be, we can use this tangent line to approximate values. Basically, it's sort of like saying that, all right, if I'm trying to look for something, instead of trying to hit it exactly, I'm just going to sort of, I'm going to give it kind of a, I don't know what I want to say here. It's like almost like a low resolution approach, right? Instead of doing an actual curved surface, you're doing a bunch of lines stacked on top of each other. So, any question?
What value was that tangent line for?
Sorry, it was for 4. The tangent line was at 4 because 4 is something we knew.
I don't understand what the point of doing that is, as opposed to just taking the tangent line of 4.1 and
well, what's
the exact value?
If you want to figure out what so the problem is that so f prime of 4.1 would be 1 over 2 times the square root of 4.1, which asks us to solve the problem that we're trying to solve anyways, right?
Right, that makes sense.
Yeah. So if you're imagining a world in which you don't have a calculator, like obviously if you want to approximate the square root of 4.1, you just plug it into a calculator, right? But there are sort of quick mental ways of couching this idea, of saying like, okay, well, if you're pretty quick with derivatives, you can do approximations for something like this really quickly without a calculator. It's how, if you've ever met somebody that's really good at estimating like cube roots in their head, most of them use a linearization technique. Though there's not that many people in the world that have any need to do something like that. So, here we are. This is not a hyper applicable thing. It is nice, however, as that specialized case of power series, because power series lets us do this sort of thing, but removing the restriction of just using a tangent line, we allow ourselves to have sort of, in a sense, like a tangent curve. It's no longer really a tangent anymore, but we use polynomials then to approximate other functions, and that actually works out. As we all know, polynomials are fantastic to do calculus with. We love taking the derivative of polynomials because they're so much easier to deal with than anything else. So it would be nice if everything could be that way. Did that answer the question, Isaiah?
Yeah.
Let's do another quick tangent line approximation. So let's use the linear approximation for f of x equals sine of x at x equals 0 to approximate sine of, let's say, 0.1. So the tangent line to sine at theta equals 0, or at x equals 0, is, so sine of 0 is equal to 0. So it'll pass through 0, 0, the origin, right? And the slope of the tangent line is, so f prime of x is cosine of x, and f prime of 0 is cosine of 0, which is 1. So our linear approximation is just a line y equals x. Where's my actual mouse? Hold on. So this time here's sine of x, and here's our tangent line. So we can then use this to approximate sine of a small angle, right? It turns out that sine of a small angle is just equal to that angle. So, or is approximately equal to that angle. Sine of 0.1 then is approximately equal to 0.1. And if we use a calculator, we get an approximation of 0.0998, which seems pretty good.
When you get a chance, will you... Oh, my bad.
Question? Adina, did you have a question? Sorry. Okay, I'm assuming that she was talking to someone else then.
Sorry, yeah, it's just lagging for me. Will you just... Oh, my bad. It's lagging a lot, and I don't know if my audio is coming through okay. Will you just scroll up really quickly for just a second in one...
Does that work? Okay. So another thing that's a nice application of derivatives that is, it's sort of it's something we've talked about a little bit before this point, but we haven't spent a ton of time on, is called a differential. And we're about to head into integration. And in integration, the idea of a differential is going to be a really, really important concept. It's going to be something that we're going to use when we're talking about integrals and how to do integrals. So differentials. So given a function, y is equal to f of x, we call dy and dx differentials. And the relation between dy and x is dy is equal to f prime of x times dx. So in sort of English terms, instead of using sort of a mathematical statement like this, a differential represents a really, really, really small, infinitesimally small change in a variable. Okay, so a differential represents a very, very infinitesimally small change in a variable. So when we write dy is equal to f prime of x dx, so for example, if y is equal to x squared, then dy is equal to 2x dx. Okay. By that we mean a very small change in y is 2x times a very small change in x. So this is basically our way of saying that like dx we're imagining as being some very small change. We could give it some like body and have like a larger change in it, right? And then essentially dy would be whatever the value of x is. We're going to multiply that by 2, and then we'll multiply that by however much we changed x by, and that'll tell us how much we changed y by. Okay. And as a side note, this is actually something that also comes really naturally out of Leibniz notation for different derivatives. If we divide both sides of this, dy equals 2x dx. If we divide both sides by dx, by some very, very small change in x, we get our familiar dy over dx is equal to 2x. And this is how Leibniz defined the derivative as the ratio of differentials. Again, this is something that we mentioned at the very beginning of class when we were first talking about derivatives and notations. But because differentials are going to come back again in just a little while when we start talking about integrals, I think it's worthwhile to cover them too. Any questions about what a differential is? Okay. The last application of derivatives I want to talk about today is one that's actually this one's a I wasn't sure if I wanted to cover this or not. You'll see it again in Calculus 2. But it's a really nice thing to have, and it helps us a lot with a lot of annoying limits. Okay, and it's called L'Hopital's rule. Sometimes you see it as La Hospital's rule. It is pronounced Hopital. He's a French guy, predictably. He might have been Swiss, actually, now that I think about it. But his name is certainly French. And it's a way of determining limits when we have indeterminate forms. Okay, so L'Hopital's rule. So if you have a limit such that plugging in your values to evaluate with continuity yields either the limit as x approaches a of f of x over g of x is equal to 0 over 0, or the limit as x approaches a of f of x over g of x is equal to infinity divided by infinity. Well, really it's plus or minus infinity over plus or minus infinity. Then in the we have that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. Essentially what this means is that this really does put the cart before the horse, because it lets us evaluate limits of 0 over 0 type as derivatives, using derivatives. So in particular, remember that when we did the definition of the derivative, all of those limits were types that ended up being 0 over 0. Theoretically, if you had a definition of the derivative problem, you would be able to use L'Hopital's rule to then find the value of that limit. You shouldn't ever do that, because in that situation it literally is you're using the fact that you can do the derivative to prove that the derivative even exists, and you can do the derivative in the first place, which is really backwards. However, L'Hopital's rule is a really helpful shortcut to remember. The proof of it is it's pretty messy, and it's really long, and it requires way more stuff than we have in this class, so I'm not even going to try to prove it. I'm basically just going to state it as a fact, and show you a handful of situations in which you could use it. So there is, for example, do you guys remember the limit as x approaches 0 of sine of x over x? Because that was one of those weird sign limits that we needed to remember, right? And it was indeterminate, and it was annoying, and you just had to memorize this rule for it. Well, L'Hopital's rule lets you evaluate this without having memorized that rule. So in particular, note sine of 0 over 0 is equal to 0 over 0. So L'Hopital's rule, LHR, applies. So LHR yields that the limit as x approaches 0 of sine x over x is equal to the limit as x approaches 0 of cosine x over 1. But that's just cosine of 0 over 1, which is 1. So you're taking the derivative of the top, and you're taking the derivative of the bottom, and it just gives you the limit. And we know that limit is 1 from earlier. You can also use this for rational function type limits. It's always going to be faster to just remember the rules for rational functions, and those are still just useful to know. So I would never recommend using L'Hopital's rule. If you have so note sometimes L'Hopital's rule requires repeated applications. For example, if we wanted to use L'Hopital's rule to evaluate the limit as x goes to 3 of x squared plus x x squared minus x plus 6 over x squared minus 4x plus 3. Should be a minus 6. No. Why did I even do that? Let's do x goes to infinity of this. Then we could use L'Hopital's rule to take the derivative. This is equal to the limit as x approaches infinity of 2x minus 1 over 2x minus 4. But that still ends up being 0 over 0, or infinity over infinity. So we can apply L'Hopital's rule one more time. To get that the limit as x approaches infinity of x squared minus x minus 6 over x squared minus 4x plus 3 is equal to the limit as x goes to infinity of 2 over 2, which is 1. Again, this is a lot of overkill. Why would you do that many derivatives when you could have just said that it was 1 because it's a rational function with power 2 on top and power 2 on the bottom, and the leading coefficients are both 1. So you do not have to use L'Hopital in every case. There are some indeterminate forms that we also see that are equivalent to 0 over 0 or infinity over infinity, but don't look like it immediately. So 0 over 0 and infinity over infinity are not the only indeterminate forms. We also have 0 times infinity. We also have 1 to the power of infinity. We have 0 to the power of 0. We have infinity to the power of 0. And we have infinity minus infinity.
Wait, 1 to the power of infinity is indeterminate?
It can be. Yeah. If it's actually the number 1 to the power of infinity, then no. But if it's something that approaches 1 to something to the power of something that approaches infinity, then it is indeterminate.
Okay.
I don't have an example of that right off the top of my head. But the trick to evaluating these can be evaluated using L'Hopital's rule, but you must rewrite them. as either 0 over 0 or infinity over infinity before applying LHR. So, for example, one of the ways we could do this, or one example of a situation where this sort of thing applies is what is the limit as x approaches 0 from the right of x times ln of x. The only reason that we're specifying a one-sided limit here is because ln of x it only has a one-sided limit at 0, right? It doesn't exist on the left-hand side of 0, so we need to only apply the right-hand limit. Well, if we try to evaluate by plugging in, what we end up with is, so if we plug in, we get that the limit as x approaches 0 from above of x times ln of x is equal to 0 times negative infinity. Right, ln of x has that vertical asymptote at x equals 0, where it goes down to negative infinity. So this is indeterminate. But it's not indeterminate in a way that we can write using L'Hopital's rule. So how can we rewrite this? Well, we can do something a little bit annoying with the x. We can rewrite this as the limit as x goes to 0 of 1 over x times ln of x. Or in other words, this is the limit as x approaches 0 from the left of ln of x over 1 over x. And now this is infinity over infinity form. Right? We've got the limit on the top goes to negative infinity, and the limit on the bottom goes to positive infinity. So now we can apply L'Hopital's rule. And if you are using L'Hopital's rule to evaluate a limit, you should note that you're using L'Hopital's rule. Just write an LHR when you apply it to make sure that whoever is looking at your work knows that you're applying L'Hopital's rule. So here we're going to take the derivative of the top. The derivative of ln of x is, of course, 1 over x. And the derivative of the bottom, which will be negative 1 over x squared. And this is still infinity over infinity, but we can cancel some stuff here, right? In particular, we can cancel the 1 over x with one of the 1 over x's on the bottom. And we end up with, we pull the negative sign out front, we get 1 over x, which is actually, sorry, this limit is still there, we haven't evaluated. Over 1 over x, which is equal to the limit as x goes to 0 of just negative x, which is in fact 0. So ln of x over, or x times ln of x does in fact go to 0 as x goes to 0. So x ln x, we can see that in this graph here. Actually, this calculator is wrong because it was undefined there for a split second. Yeah. It's confused by whether or not it's defined or undefined, but it should be undefined as 0, 0. The limit certainly is 0 from the right, though. So anytime you have 0 times infinity, note that for 0 times infinity type limits, we can rewrite as 1 over 0 times infinity, which is infinity over infinity. So you can take the one that goes to 0, take its reciprocal, the reciprocal of 0. The reciprocal of 0 isn't infinity, but generally if you have a limit that's going to 0, the limit of its reciprocal will go to infinity. And then you have something in L'Hopital form, and you can use L'Hopitals on it.
What
Yes.
what's the bottom symbol under infinity is equal to?
This one here,
Yes.
that is a very bad infinity.
Thank you.
Yeah. All right. The other types of indefinite forms can be dealt with in a slightly different way. So for the forms, 1 to the infinity, 0 over 0, 0 to the power of 0, or infinity to the power of 0, we need a different trick. So let's do another example. Let's do the limit as x approaches infinity of x to the power of 1 over x. And this one is of the variety, this is infinity to the power of 1 over infinity, which is infinity to the power of 0, indeterminate. For this sort of thing, we're going to need to use a logarithm, right? So let's say for a second that y is equal to x to the 1 over x. Then ln of y is equal to ln of x to the 1 over x. And ln of y is equal to 1 over x times ln of x. In other words, ln of y is equal to ln of x over x. So now we can apply our limit again. The limit of ln of y is equal to, as x goes to infinity, is equal to the limit as x goes to infinity of ln of x over x. And the right-hand side of this is now L'Hopital's. That's infinity over infinity. So we can apply L'Hopital's rule. So the limit, it turns into the limit as x approaches infinity of 1 over x over 1, which is 0. But there's a problem. That was the limit of the natural log of y, not the limit of y. So the limit as x goes to infinity of the natural log of y is equal to 0. So what we actually need to do here is we need to apply e to both sides. So the limit the limit as x approaches infinity of y is equal to the limit as x approaches infinity of, or e to the limit as x approaches infinity of ln of y, which is e to the 0. So y the limit as x approaches infinity of x to the power of 1 over x is in fact basically what you're doing here is you're taking the logarithm of your limit, and then at the end you're doing the limit, and then you're doing the limit inside of the logarithm, and then you're raising it to, you're doing e to the power of that. So to evaluate the limit as x goes to infinity of x to the 1 over x, we're really doing e to the limit of as x approaches infinity of ln of x to the 1 over x, which is e to the limit as x approaches infinity of ln of x over x, which is e to the 0, which is, well, then we apply our L'Hopital's rule. So we get e to the limit as x approaches infinity of 1 over x, which is e to the 0, which is 1. And more or less, this is the same exact trick that you're going to use for all limits of that type, of the type 1 to the power of infinity, 0 over 0, or 0 to the power of infinity. You're going to take a logarithm. That will turn that into something that's either 0 over 0 or infinity over infinity once you use your log properties, and then you're going to take a, you're going to do e to the power of both sides. So I guess the last case that I didn't really mention is the infinity minus infinity case. This one is almost always finding a common denominator. So, for example, the limit as x approaches infinity of 1 over x minus 1 over x squared is infinity minus infinity. So we need to transform it into something that's L'Hopital's rule. So we get the limit as x approaches infinity of x over x minus 1 over, or x over x squared minus 1 over x squared, which is the limit as x approaches infinity of x over, or x minus 1 over x squared. And this is not a limit that requires L'Hopital's, but we can apply it anyways. So that's 1 over 2x, and this is in fact 0. Oh, I'm stupid. This was this. This was not an indeterminate limit to begin with. If you change it to be the limit as x approaches 0 from the right, then it is indeterminate. And in this case, we get the thing that's actually true, which is that this is actually infinite. If we graph it, 1 over x minus 1 over x squared, you'll see that it does in fact still go off to infinity, negative infinity. This is what I get for pulling an example off the top of my head in the middle of class again. Not 100% sure why this one should be negative. Is 1 over x squared. Yeah, so if x is less than 1, then x squared should be bigger than, or it should be smaller than x. So 1 over x squared should be bigger than 1 over x, so it should definitely be negative. And so between linearization, differentials, and L'Hopital's rule, that just about rounds out everything that we're planning on doing with derivatives for now in this class, other than the fact that we're going to be using derivatives for integration. But this caps off the amount of content that will be on your exam next week. So, the exam will cover related rates, which we did a little bit of. So we did related rates before break. So maybe on on Tuesday we'll spend some time doing a little bit of related rate stuff just to refresh everybody. And I know Katie did some related rate stuff in some of her recitations. We have applied optimization, or curve sketching, and then applied optimization. So using the first and second derivative to construct good models of what a curve should look like, and then also using first derivative and second derivative tests alongside absolute maximums and minimums to solve applied optimization problems. And then we have these 3 quickies: linearization, differentials, and L'Hopital's rule. So, I will post some questions for you guys to work on, and yeah, I will hang out for the next about hour and a half if you have any questions. So, but otherwise, I will see you guys on Tuesday. We'll do a little bit of review, and then I'll hand out the test around 1 o'clock. Any questions before I let you guys go?
Thank you, Aaron.
Thank you.
No. Thank you for your time.
All right. I will get the lecture notes up as well as the video up as soon as I can, and I will post some questions before that. So,
Not as if it was a competition or anything, but